First thing is we're looking back at all the stuff we've done. We're in the middle of, we're just starting actually, section 8.4 on the famous alternating series test. Before we get started, let's write down the things that you're actually supposed to know at this point. Well, whether you do or not, it's questionable, but it's kind of important because this is a very large memorization chapter. And if you don't know it, then you're in deep trouble at this point. And again, the best way for you guys to actually study this material is going back to old school, and that means flashcards, like you used to when you were in kindergarten and first grade when you were learning multiplication tables and addition, subtraction, and division. You used to flashcard yourself to get this stuff basically memorized. But with these flashcards, you need to do a couple of things. You need to figure out the name. For example, if we're doing a test, the name of the test and exactly what it says. And then right underneath that, you should study an example of this test being used. Because when we get to the problems that we're going to be doing, you're going to use it to prove stuff. And you got to write it a certain way. So you got to get familiar with how you're using these tests to actually prove stuff. So you need examples of these tests and actions, and that's what you study. And after you do one or two examples, you begin to catch a pattern, hopefully, that you do the same thing over and over again. So let's talk about stuff you're supposed to know. We're talking about series. Let's talk about name series you have memorized and recognized. The first one is the geometric series. The next one is telescoping series. In terms of name series you should recognize, we actually give it a name, a harmonic series. But then from the harmonic series, we extend it out and talk about what kind of series? P series. These are name series that you're supposed to know. Inside and out. You're supposed to recognize the geometric series. It's the sum of a number raised to a power of n. Maybe times a constant, but that's pretty much what you got. Telescoping series. It's a fraction minus a fraction where the numerators are the same. So when you have this idea of when you subtract, the terms end up canceling themselves out. And most important on a telescoping series, the terms have to decrease. A harmonic series, famous. The sum as n goes from 1 to infinity of 1 over n. And what does the harmonic series do? Diverges. And then you got a p series. P series is the sum of 1 over n to the p. Where p happens to be greater than 1, the series is going to converge. If p is less than or equal to 1, it's going to diverge. Let's talk about your name test that you have memorized. That helps us prove a particular series is either going to converge or diverge. The first one, these guys are in order as we number them. Number 1 is called the divergence test. If you got a series and you notice the sequence part and you take the limit as n approaches infinity of the sequence part and you don't get 0, automatically the series is going to diverge. Divergence test. Your second test was what? Integral test. What was the integral test? Well, if I convert a series into an integral, it is calculus too for all. So if you think about it from that concept, and as long as the function is positive, decreasing, and continuous, when I integrate, if this integral converges, the series that it came from converges. If the integral diverges, the series that it came from also diverges. They do the same thing. Number 3, we had the direct comparison test, the DCT. Direct comparison test. But you had to get the inequality just right. If you've got an unknown series and you're comparing it to a known series. If the known series converges and the unknown series is less than or equal to the known series, that converges, then the unknown series is going to converge. And if you got an unknown series compared to a known series and the known series is known to diverge and you can get the unknown series to be greater than or equal to the known series that diverges, then the unknown series is going to diverge. But you had to get that inequality just right. And then from there, we went into test number 4, which was the limit comparison test. So again, you're comparing two series, an unknown series to a known series. And when you take the limit as n approaches infinity of the ratio of the unknown series sequence part to the known series sequence part. And you take your limit as n approaches infinity, and you get a, quote, constant, a number that is not zero, and it's not infinity. It's got to be a finite number that's not zero. Then the two series are going to do the same thing. Whatever you compared to, if you knew it converged, then the unknown series converges. If the known series diverges, then the unknown series is going to diverge. So they do the same thing. And then the last one that we are discussing today, and we just started it last time, is the famous AST, which is the alternating series test. And I'm going to pick it up from there. So, alternating series. An alternating series is the form that looks like this. The sum as n goes from 1 to infinity of negative 1 to the n times bn. So you got this negative 1 to the n, or you can write it sum as n goes from 1 to infinity of negative 1 to the n plus 1 times bn. It's some kind of negative 1 to a power of n, whether it be n or n plus 1 or even n minus 1. This is an alternating series because you got that plus, minus, plus, minus, plus. But don't forget this guy. This is the fancy way of writing an alternating series. That is the sum as n goes from 1 to infinity of the cosine of n pi times bn. Now, this is an alternating series. The alternating series test says this. If you're given an alternating series, which is the sum as n goes from 1 to infinity of this negative 1 to the n plus 1 times bn, you're going to focus on the sequence part without the alternation. This is the bn part. And two things have to happen. If, number one, the bn plus 1 is going to be less than or equal to the bn for all n, which means when you plug n equals 1, n equals 2, n equals 3, it's got to be monotonically decreasing. b1 is got to be greater than or equal to b2, which is going to be greater than or equal to b3, greater than or equal to ... all the way down the line. You're going to have to be decreasing. The terms have to go down. And this is what you need to show me. And if, number 2, you take the limit as n approaches infinity of the bn, which is the sequence part of your alternating series without the alternating aspect on it, and if you take the limit as n approaches infinity of this sequence part and you get 0, then the sum as n goes from 1 to infinity of negative 1 to the n plus 1 bn, the alternating series is convergent. If any aspect of this fails, okay, if it doesn't go to 0 or the terms don't go down, they actually go up, they increase instead, then the series is going to diverge, okay? So we would say otherwise it's divergent. This is your alternating series test for an alternating series. So again, we discussed this last time, so we'll go back to our notes. So here's our notes, and we had all this awesome pre-section video. And please, when you're watching the videos, take notes off the examples and stuff. This is why we type these examples up here for you guys. So, and we did several problems on the video there. So, and we talked about the concept last time in terms of algebra, how to tell when a function is decreasing or increasing. If you have to prove it, you have to basically go for that first derivative of your function and show that the slope or the first derivative is negative, and that interval makes the function decrease. So this is where we picked up last time, and we just got to do one example last time, so let's pick it up from there. So again, just restating what I stated up here, this idea of the alternating series test. You've got an alternating series, which is that sum as n goes from 1 to infinity of negative 1 to the n, or n plus 1, or n minus 1, whatever, times bn. And so when you write this out, it'll be b1 minus b2 plus b3 minus b4, that plus minus alternating series. And you focus on the bn part. And if the terms decrease and the limit of the bn as n approaches infinity goes to 0, then the alternating series is going to, quote, converge. If those two pass, it converges. Otherwise, it's going to diverge. Okay? So we looked at this one last time, which throws a lot of people off because The sum as n goes from 1 to infinity of negative 1 to the n plus 1 over n. You look at this thing and you go, that's the harmonic series. No, it is not. Harmonic series is just the sum as n goes from 1 to infinity of 1 over n. This has got something special added onto it. It's negative 1 to the n plus 1 divided by n. And because of that alternating part that you add, then subtract 1 minus a half plus a third minus a fourth plus a fifth, dot, dot, dot. The terms decrease. They go down as you plug in numbers. And the limit as n approaches infinity of the bn part, which is the 1 over n, gives you 0. Then by the alternating series test, this is actually a convergent series. I mean, if you didn't have the alternating part on it, it would actually diverge. It would be the harmonic series. But by putting the 1 minus a half plus a third minus a fourth, that aspect of that you give and then you take some of it away, you actually get a convergent series out of it. So let's take a look at this next guy. Ken. What kind of series is it? It's the sum as n goes from 1 to infinity of negative 1 to the n times 3n divided by 4n minus 1. It is an alternating series. Special case here, alternating series. So with this alternating series, we're going to use the alternating series test. So, alternating series test. You first analyze the bn part, the part without the alternation, the sequence part of your series without the alternation, which is the 3n divided by 4n minus 1. We're trying to prove this thing is either going to converge or diverge. The first thing I'm going to do is I'm going to test to make sure the terms are decreasing. So as this is bn is equal to 3n over 4n minus 1. I show decreasing by plugging in this thing. The series starts at 1. Okay? So starting at 1, I plug it in, then n equals 2, then n equals 3, dot, dot, dot. Plugging in 1. 3 times 1 is 3, divided by 4 times 1 is 4, minus 1 is 3. It's 3 over 3. Now I'm going to plug in 2. 3 times 2 is 6, over 3 times, 4 times 2 is 8, minus 1 is 7. I'm going to put in 3. 3 times 3 is 9, over 3 times 4 is 12, minus 1 is 11, comma, dot, dot, dot. I went from 1 to 6 sevenths to 9 elevenths. These terms are decreasing. They are going down. That's a check. That part holds. But then there's the second part. You're going to take the limit as n approaches infinity of the bn. This will be equal to the limit as n approaches infinity of 3n over 4n minus 1. What do I get when I take the limit as n approaches infinity of 3n divided by 4n minus 1? You should be able to look at this thing from calculus 1 and tell you what the answer is. What is it? 3/4. The degree of the top is 1, degree of the bottom 1. The answer is the ratio leading coefficient is 3/4. And that's a problem. Because according to the alternating series test, if this thing is going to converge, what does the limit have to be? 0. This is not equal to 0. So this part failed. Therefore, the series, the sum as n goes from 1 to infinity of negative 1 to the n times 3n divided by 4n minus 1 is divergent by the alternating series test. Does that make sense? Just one of those two aspects, part 1 or part 2 fails on the alternating series test, you have a divergent series. They both have to pass. The terms have to decrease, and the limit of the sequence part without the alternation must go to 0. Then the alternating series converges. Take a look at this next guy. The sum as n goes from 1 to infinity of the cosine of n pi times n over n cubed plus 1. Now this is a problem you have to kind of train yourself to notice. Hey, it's cosine n pi. What does that mean? Well, that means it's alternating. So this is an alternating series, so I shall use the alternating series test. The bn part, the sequence part of your alternating series without the alternation, the cosine of n pi is your alternating part. It's n over n cubed plus 1. This is the alternating, the sequence part without the alternation. So we're going to check it out. Number 1, I'm going to take basically make sure the decreasing aspect. So I'm going to plug in n equals 1, n equals 2, n equals 3, n equals 4. Just got to show me that these terms go down. Plugging in 1, I get 1 over 1 cubed is 1 plus 1 is 2. Plugging in 2, I can get 2 over 2 cubed is 8 plus 1 is 9. Plugging in 3, I'm going to get 3 over 3 cubed is 27 plus 1 is 28. Plugging in equals 4, I get 4 over 4 cubed, which is what? 64 plus 1 is 65. Dot, dot, dot. My terms, look at the fractions, they're clearly decreasing. Check. Second thing you got to show me is I need to take the limit as n approaches infinity of the Bn. Let's see what we get. This will be the limit as n approaches infinity of n over n cubed plus 1. Just because I want to show you some stuff here. When I plug in infinity, I get infinity over infinity cubed, which is infinity plus 1, which is infinity. So to show my work, L'Hopital's rule. So this would be equal to the limit as n approaches infinity of, derivative of the top, derivative of n is 1, derivative of n cubed plus 1 is 3n squared. When I plug in infinity, this will be 1 over 3 times infinity squared. 1 over infinity is 0. It converges to 0. Dr. Taylor, did we have to do all that L'Hopital rule on this one? No. If you notice the degree of the top is less than the degree of the bottom, we'll give you that one. But it's a great time for L'Hopital's rule. But you've seen problems in the past where it's not so obvious. When it's not so obvious, I do expect to see a L'Hopital rule or something like that on those problems. Okay? So like that sign of 1 over n divided by 1 over n, you had to show me L'Hopital rule on that particular problem. But this one, no. But I just want to show you that 0. Therefore, the terms decrease, the limit goes to 0. So what can you tell me about this series? Sum as n goes from 1 to infinity of the cosine of n pi over, times n, over n cubed plus 1 is convergent by the alternating series test. Does that make sense? You're proving to me, not just, oh, it converges. No, I'm not going to take it converges. No work, no credit. You got to prove it to me. So being an alternating series, I used the alternating series test. So I had to pass both parts of the test. And since it does, this series is going to converge. If it fails just one of them, series diverges. Does that make sense? Okay. Now, this next one is this. We know so much about alternating series, we're going to dive into this one a little bit deeper than we have any other type of series. And we have something called the alternating series estimation theorem. This is the alternating series estimation theorem. So more stuff on this. By the way, chapter 8.4 is a very large chapter, to let you guys know. So, it says this. If the sum S equals the sum as n goes from 1 to infinity of negative 1 to the n, in this case we did minus 1, times Bn, an alternating series that satisfies these two concepts. If the Bn plus 1 is less or equal to Bn for all n, aka the sequence decreases, and if you notice that the limit as n approaches infinity to the Bn goes to 0, well, first off, what does this tell me? By the alternating series test, this series is going to do what? Converge. So if you've got a convergent alternating series, then here's the deal. The absolute value of Rn is equal to the absolute value of S minus Sn, which would be less than or equal to Bn plus 1. Now, what does that mean in actual English? It means this. We're trying to figure out where these things are going to converge to, what they're going to add up to be. Now, we know there's only two series that doesn't require much work for us, just got to get them into a form, that we know exactly what the series adds up to be, what it converges to. That is a geometric series and a telescoping series. That was chapter 8.2. After that, we just changed the tune. We just started giving you guys a series and just saying, hey, look, can you tell me if this thing is either going to converge or diverge? That's what all these tests have been since then. Does this series converge or diverge? But we're still interested, if it converges, what is it going to add up to be? Now, this is an alternating series. We know when it's going to converge. So, but here's going to be my problem. You see that little Rn? Rn is this. You've got S, which is your true sum. S is the true sum. This is the sum as n goes from 1 to infinity of this negative 1 to the n minus 1bn guy. But then we're going to compare this to this guy. We're going to call him S with a big N on him. This was that partial sum we did way back when in chapter 8.2. Partial sum. So, look, most of you guys are engineers in here. And mathematicians, engineers, and all science, all STEM folks, they're inherently lazy. Look, it's an infinite series. Do you want to add up an infinite number of stuff? No, it takes too long. So what do you want to do? Well, after a while, you're just going to give up and declare victory after adding up so many. That's called a partial sum. So you're going to sum as n goes from 1 to whatever this big N is of this negative 1 to the n bn. This is a partial sum. This guy will approximate S. It's not going to be, there's going to be some rounding off error here because we're going to, after a while, just declare victory after about, 50 decimal places. Good and close enough, declare victory. We're going to get within our tolerance range. Classic engineering here. So we got to get within our tolerance. So the true sum is equal to this partial sum plus Rn. This is going to be the remainder. What is left over after you decide to, okay, instead of adding it up to the first 100 million of these things, this game's going to infinity. Instead of doing that, I'm going to give up after adding up, 50 of them. I took a pain to do just adding up 50 of them. After that, we're going to declare victory on it. So you find out your S50, what you basically add it to 50, plus whatever the remainder is. The rest of it will actually be equal to the true sum of this guy, which is typically unknown. But this is called the remainder, or the error on your partial sum. And what this alternating series estimation theorem says is basically this. Your estimation of the remainder after n terms, which is equal to the true sum minus your partial sum, will be less than or equal to bn plus 1. We're going to be focusing on the error, how much off your answer is. Okay? And it's a formula. So Rm is less than, which is equal to the true sum minus the partial sum, absolute value, is less than or equal to bn plus 1. So if you added up the first n terms, your biggest error is going to be with the next term up because it's an alternating series. Alternating series. Remember, you've got the sum of this negative 1 to the n bn stuff here is going to be b1 minus b2 plus b3 minus b4 plus dot dot dot, and it's plus b whatever you want to stop it at, right? But officially it keeps on going. Minus bn plus 1 plus bn plus 2, and it keeps on going forever. But if you stop it in right here, in terms of absolute value, this is where the biggest error is going to be at. Because after that, you're going to take away a little bit, you're going to add a little bit, you're going to take away a little bit. So this will be the biggest error. This is where the max error occurs at. That's what the alternating series estimation theorem says. Since it's alternating, once you cut it off, the next term up is going to be the biggest error because after that, then you're going to take away a little bit. Then add a little bit more. Then take away a little bit more. And then see, it keeps zeroing in on what this thing's going to converge to. So that's where you get the bn plus 1. If you cut it off at n, your error will be at the next term up. That's what the alternating series estimation theorem says. So let's take a look at this guy here. Example. We got the sum as n goes from 1 to infinity of negative 1 to the n divided by n. Determine whether the series is convergent or divergent. Well, number one, it's an alternating series. Therefore, I shall use the alternating series theorem test. The alternating series test. Here in this problem, the bn, the sequence part without the alternation is the 1 over n. I'm going to test two things. Number one, I got to test for decreasing. This series starts at 1, so n equals 1, n equals 2, n equals 3, dot, dot, dot. When I plug in 1, I get 1 over 1. If I plug in 2, I get 1/2. Plug in 3, I get 1/3. Pretty easy, you can catch the pattern. They clearly are decreasing. And number 2, I'm going to take the limit as n approaches infinity of the bn part. This will be equal to the limit as n approaches infinity of 1 over n. And the limit as n approaches infinity of 1 over n is 1 over infinity, which is 0. The terms decrease and the limit goes to 0. Therefore, by the alternating series test, The sum as n goes from 1 to infinity of negative 1 to the n times 1 over n is convergent. But you really shouldn't be surprised by that fine fact. We did this problem last time. Okay? So this is a convergent series. Now, the next part is this. We're supposed to calculate the partial sums from S5 through S8. What is S5? S5 is you guys actually adding up the first 5 terms of the series. So n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. I'm going to add them up. So here's my series up here. So plug in n equals 1. Negative 1 to the first is negative 1 over 1. Plus, plug in n equals 2. Negative 1 squared is 1 over 2. Plus, plug in the next one. Negative 1 cubed is negative 1 over 3. Plus, plug in 4. Negative 1 to the fourth is 1 over 4. Then you plus plug in 5. That'll be negative 1 over 5. And you stop at 5 and you add it up. To grab for a handy dandy calculator. So this would be, typing it in, negative 1 plus 1/2 minus 1/3 plus 1/4 minus 1/5, end up getting negative 0.783333. Does that make sense? That's S5. What is S6 going to be? S6 would be adding up the first 6 terms of your series. And this is for your benefit. N equals 1, n equals 2, n equals 3, n equals 4, n equals 5. Then we do one more, n equals 6. This will be negative 1 plus 1/2 minus 1/3 plus 1/4 minus 1/5. But n equals 6 would be plus 1/6. This is what I want to show you guys. What is this going to be? Well, this first part right here is actually S5, right, plus 1/6. So all I got to do is take the last answer that I put on my calculator here. In the light source, you guys can see this thing. And I'm just going to add 1/6 to this guy. When I add 1/6, I get negative 0.61666667. So knowing the pattern here, what is S7? To calculate S7, you should add S6 plus one more, n equals 7. Does that make sense? And when I plug n equals 7 into this thing, negative 1 to the 7th power is negative 1 over 7. So this is going to give me, previous answer, minus 1/7. End up getting negative 0.7595238095. And then the last one, S8, would be S7 plus one more, and that would be n equals 8. Plugging in 8 into this series up here. Negative 1 to the 8th power is 1 divided by 8, so that'll be plus 1/8. So I'm going to take this answer and then just add 1/8 to it, and I get negative 0.6345238095. S5, S6, S7, and S8. You'll notice that we seem to be zeroing in on a number here. Looks like about negative 0.6 something or other. Okay? And if you put more and more terms in this thing, you'll see the decimals start to repeat themselves. Now, look at this next one. Part C. Give an upper bound for R5. i.e. give the maximum value for the difference between R5 and between, actually, it should be S, there's a typo there, S5 and the true sum. So they want an upper bound for R5. It's the formula. R5, absolute value, is less or equal, which is equal to, equal to the true sum minus the partial sum, which is less or equal to Bn, which is 5, plus 1. So to get this upper bound, this is the formula. This is what I'm using right here. Now, n is 5. What's 5 plus 1? 6. This would be B6. Now, remember the Bn is from the alternating series. It's the sequence part without the alternation. So the Bn is 1 over n. So as Bn is equal to 1 over n, this would be 1 over n is 6. The answer is 1/6. So the error or remainder for the first 5 terms will be less than or equal to 1/6. This is the maximum amount of error that adding up the first 5 terms is going to have. Does that make sense? Adding it, remember, this is the remainder for S5. This answer right here, negative 0.78333. This answer right here is going to be at most 1/6 off of the true answer. It's always the next term up. When you do a 5, the next term up would have been plus 1/6, and that's where your error comes in at. That's the alternating series estimation theorem. Now, the big deal is coming up next. Why do you care? Look at the next problem. For the difference between Sn and the true sum to be 0.000001, to which term should Sn be calculated? Okay? Here in English, let me explain it to you. All right, you got yourself a nice alternating series. We need to estimate this alternating series. Now, I do not want to add up an infinite number of stuff. I don't have the time nor the inclination to add up an infinite number of stuff. So we're going to cut it off somewhere. But here's my problem. I got to have a tolerance of 0.000001. That's what I got to have my tolerance to be. So how many terms do I actually need to add up to get this kind of a tolerance so I don't actually have to add up to infinity? So this is what you do. We know the formula, Rn, which by formula is the difference between the absolute difference between the true sum and the partial sum, and that's less than or equal to Bn plus 1. This is my formula. And we want this to be less than or equal to my tolerance. My tolerance is the 0.000001. So this is my formula for the remainder, how much, my error, if you will. And I want that error to be less than their tolerance, less than 0.000001. Now remember, in this problem, Bn, the sequence part of your series without the alternation, is 1 over n. So therefore, Bn plus 1 would be 1 over n plus 1. Bn is 1 over n. You get that from the series. So Bn plus 1 would be 1 over n plus 1. Now, plug it in right here. So you get 1 over n plus 1 is less or equal to 0.000001. And now go solve for n. Solve for n. I'm going to multiply by n plus 1 on both sides. That gives me 1 is less or equal to 0.000001 times n plus 1. I'm going to divide by 0.000001 on both sides. And I end up getting, this will cancel. And this leaves me with the n plus 1 is going to be greater than or equal to this number here, which is, putting on the old handy-dandy calculator, 1 divided by 0.000001 is, what do we got here? 1 million. And now, solve for n. Subtract 1. N has got to be greater than or equal to, 1 million minus 1 is 999,999. So in other words, if you want a tolerance of 0.000001, you've got to add up 999,999 terms. Well, at least it's not infinity. Okay? You do have a spot that you can cut this thing off with as long as you can tell me the tolerance. Now, remember, a lot of the times you can get a crappy decimal. If you got any kind of decimal, you can't have a decimal of a partition. You can't have a decimal of a series. You always round up to the nearest whole number. This one was a nice number here, so you actually have to have 999,999 or more. You can add on more terms if you want to. You'll just be way within your tolerance range. But this is the minimum number right here, the terms you need to have to get your tolerance. Does that make sense? Question? Yeah.
Yeah, actually another question back about Part A. Why exactly did we just make it so it went over and again? Why for B and N? Why did we?
Oh, that is the from the actual alternating series and the alternating series estimation theorem. The series itself is the sum as n goes from 1 to infinity of the -1 to the n, or n plus 1 minus 1, times the bn. The bn is the sequence part of your alternating series without the alternation. So instead of calling this guy an like we did on all the other series before this, the bn is the sequence part without the alternation, and that's what you test with the alternating series test and the alternating series estimation theorem. So let's take a look at this guy here. I've got the sum as n goes from 1 to infinity of -1 to the n times 2 divided by 3 to the n. Stop, pause, hesitate, look at this thing. This dude's got a name. What kind of series is it? What's its name? What is it? Geometric series. How do you know it's a geometric series? Because look at the series. All I got in the series is a big old sum with a bunch of numbers raised to a power of n. Times a constant. We don't care about constants. Numbers raised to powers of n. That's a geometric series. So I know exactly when this thing's going to converge, if it converges at all. And we know what it's going to add up to be because it's a geometric series. And they're going to make you do that. Okay, determine whether the series is convergent or divergent. Well, all right, let's figure this thing out. Noting that it's a geometric series, we have the formula memorized. The sum as n goes from 1 to infinity of ar to the n minus 1. And we know on a geometric series that on a geometric series, the series is going to converge to, add up to a over 1 minus r if the absolute value of r is less than 1, and is going to diverge if the absolute value of r is greater than or equal to 1. So I got to convert this geometric series, because it's nothing but numbers raised to the power of n times a constant, into this format. So this is the sum as n goes from 1 to infinity of -1 to the n times 2 over 3 to the n. You notice both these two terms have an n power, so I'm going to put those together and factor out the n. So this will be the sum as n goes from 1 to infinity of -1/3 to the n times 2 officially. But according to my formula, and it's still alternating because it's still a -1 to the n there, so with that negative r, it's an alternating series. But I want an n minus 1 power, so I've got an n power. I've got too many. I got one too many, so I'm going to pull off one of them. So this is the sum as n goes from 1 to infinity of 2 times -1/3 times -1/3 to the n minus 1. Putting it together, this is the sum as n goes from 1 to infinity of putting your constants together, -2/3 times -1/3 to the n minus 1. I can tell you from this that your A is equal to -2/3. Your R is equal to -1/3, which implies when you take the absolute value of R, absolute value of -1/3 is 1/3. And how does 1/3 compare? It is less than 1. So this is a convergent geometric series. That's all it is. Determine whether the series is convergent or divergent. What is it? It is convergent. R is -1/3, which makes absolute value of R 1/3 less than 1 converges. Does that make sense? They didn't ask me, what does it add up to be? Wait, that comes in part C or something or other. But not right now. They just asked if it converged or diverged. So I'm answering their question. This thing converges. So, part B, we want you to find the partial sum S4. So to find S4, I'm going to add up the first 4 terms. Now this thing starts at 1, so I'm going to add up the first 4 terms. This is n equals 1, n equals 2, n equals 3, and n equals 4. I'm going to go back to the original series here. I'm going to plug in 1. -1 to the first is -1 times 2 is 2 over 3 to the first is 3. So that's -2/3. Plus, I'm going to plug in 2. -1 squared is 1 times 2 is 2 over 3 squared is 9. Plus, plug in 3. -1 cubed is -1 times 2 is -2 over 3 cubed is 27, plus plug in 4, negative 1 to the 4th is 1, times 2 is 2, over 3 to the 4th is 81, and that's where I stop. First 4 terms. So I'm going to add this up on my calculator here. Negative 2/3 plus 2/9 minus 2 over 27 plus 2 over 81. It is negative 0.493827165. It's web work. Give them all the decimals. Okay? That is what S4 is. Okay? Now, give the true sum, and it's supposed to be an S there, if possible. Can you tell me what the true sum of this thing is? Well, because it's a geometric series that converges, right? This thing is going to converge to the form A over 1 minus R. What was A in this problem? Well, look back. A was equal to negative 2/3 over 1 minus R. R is negative 1/3. So if I put that on my old handy-dandy calculator here, this thing is actually going to converge, if you go for the infinite series, is going to converge to, parentheses right numerator, negative 2/3, divided by parentheses 1 minus parentheses negative 1/3, close parentheses for fraction, close parentheses for the denominator. I end up getting negative 0.5. And if you look at my answer, even though I just added up the first 4 terms, I got negative 0.4938, whatever. That's even pretty darn close to negative 0.5, which is truly what it adds up to be, because it was a geometric series. Okay? They want you to do this. Find the true difference between Sn and the partial sum S4. Okay, with the true sum, that would just S there. All right? So the absolute difference here, true difference would be S minus S4 absolute value. This basically is going to be what your R4 is going to be. And so this is going to be S, which is negative 0.5, plus, or minus, negative 0.4938271605. And so this will be the absolute value of, putting this on my calculator, negative 0.5 minus negative 0.4938271605. And notice I get a negative number, absolute value negative 0.006172839.5. And absolute value of a negative is what? Positive 0.00617283951. This is the difference between the two. That's how much off my answer is. 0.006 from just S4 to actually the true sum. Now look at this last part. For the difference between the Sn and the true sum to be within 0.001, what should Sn be calculated? If I want to get this kind of tolerance, 0.001, how many terms we need to take it out to? So here we go. Remember, Rn, which is equal to the true sum minus the partial sum, is got to be less than or equal to Bn plus 1, and that's going to be less than or equal to 0.001. Your Bn, which is the part without the alternation, go back to your series, the part without the alternation is 2 over 3 to the n. 2 over 3 to the n. So Bn plus 1 would be 2 over 3 to the, replace n with n plus 1, and that's what goes here. 2 over 3 to the n plus 1 is going to be less than or equal to 0.001. Now you need to solve this guy. Very quickly, I'm going to move this over here and divide by this. So there'll be 2 divided by 0.001 is less than or equal to 3 to the n plus 1. I got the 3 to the n plus 1 by himself. The variable that you want to solve for, n, is in the exponent. What gets rid of exponents? What brings down exponents? What do you got to do to solve for exponents? Logarithms. I'm going to take the natural log of both sides, just to remind you of some basic math here. And so, and the exponent goes out front, so the natural log of 2 divided by 0.001 will be less than or equal to n plus 1 times the natural log of 3 when you put the exponent out front. Divide both sides by the natural log of 3. You end up getting this. I'm going to put it on my calculator. Natural log of 2 divided by 0.001, close parentheses, that divided by the natural log of 3, and I get 6.918639 whatever is less than or equal to n plus 1. So you've got to solve for n. Subtract 1 from both sides. You get 5.918639 is less than or equal to n. But remember what I said about n's. You can't have a 0.9 whatever. I don't care if it's a 0.0 whatever. You cannot have a decimal of a partition or a sequence. So what's my number? How many terms do I need to take it out to? 6. Always round up. The answer is 6. I need to take out 6 terms if I want to get this sign of tolerance. Does that make sense? All right. Last thing is I promised you guys we got a very short quiz. Should take you about 2 seconds to do, but we're passing this thing out. So I want to see if you guys actually know some stuff. So clear off your desk. No notes, anything, just a piece of paper and a pencil. The paper we're passing out and a pencil, and take the quiz. And I'll see you guys on Monday.